Welcome to section 6.5 on the central limit theorem. So the key concept in this section is we're going to learn about the central limit theorem. So the central limit theorem tells us that for a population with any distribution, doesn't matter if it's a normal distribution or some other type of shape in terms of the data, the distribution of the sample means approaches the normal distribution as the sample size increases. So to break that down, basically, as your sample size increases, your sample mean data gets closer and closer to that normal distribution, that bell-shaped curve. So the procedure in this section forms the foundation that we're going to use in later chapters for estimating population parameters and for hypothesis testing. So it's an important section to cover. Okay, some things about the central limit theorem, some givens. The random variable x has a distribution, which may or may not be normal, with a mean and a standard deviation. And these are the symbols for those. And the simple random samples of all of size n, whatever n may be 10, it may be 20, doesn't matter. It depends on the example, but that n stands in for the number of people that you're going to sample. And they're selected from the population. And the samples are selected so that all the different combinations of the same size n have the same chance of being selected. So if my n is 10, I should be selecting my group of 10 in a way that it doesn't really matter which group of 10. Each person that's in that population has the same chance of being chosen to be part of my sample. Okay, so where does that bring us? So the distribution of the sample mean, so again, this is the symbol for mean, we learned that earlier in the course, will, as the sample size increases, approach the normal distribution. So again, your sample mean is going to approach that normal distribution as your sample size increases. The mean of the sample means, so now we don't just have a sample mean, we actually have a mean of sample means, is the population mean. So for instance, your sample is drawn from your population. So if you take a number of different samples and you calculate the mean of those means, that is going to actually equal your population mean. And the standard deviation of your sample mean is your standard deviation divided by the square root of n. And that n, just as we were just talking about, is the number of people that, the number of samples. Okay. So how do we actually use this? Some practical rules. So for samples of size n larger than 30, so meaning that you have more than 30 in your sample, the distribution of the sample means can be approximated reasonably well by a normal distribution. So what that means is that bell-shaped curve does a pretty good job of showing the distribution of the sample means as long as your sample size is larger than 30. And the approximation becomes even closer to a normal distribution as the sample size goes up. So not just 30, 40, 50, 100, 200. The larger your sample size, the closer and closer that is going to be to that normal distribution. Secondly, if the original population is normally distributed, then for any sample size n, the sample means will be normally distributed, not just values of n that are larger than 30. And that's because your sample is drawn from your population. So if you know your population is normally distributed, then it's going to follow that your sample mean would also be normally distributed because it comes from that population. Okay, some notation. So the mean of the sample means, I know, a lot of means to talk about, but again, you have a sample mean, and if you had multiple samples, you could take the mean of those sample means. You'd add them together and divide by the number of sample means that you had. So in this case, your sample mean, which is what this guy is, equals your mean. So there's not really anything that you need to do there. You can use the mean that's given to you in the problems and assume that mean is the same as your mean for your samples. And the standard deviation of a sample mean, which is this symbol here, is your standard deviation that will be given to you divided by the square root of the number of samples. And this is often called the standard error of the mean, but for now we're not going to talk more about standard error. Okay, so let's look at some examples of this. So these are some graphs that kind of illustrate the point that as you increase your n, or the number of samples, the closer and closer you will get to that normal distribution. And so this is really more interpreting graphs in this particular section. So let's read what they have here. So as we proceed from n of 1 to n of 50, so here's our n of 1 and down to our n of 50, we see that the distribution of the sample means is approaching the shape of a normal distribution. Okay, so let's look here. So this is our n equals 1. You can see that there's not really a great shape here. You know, it kind of goes up and comes down the other side, but it's sort of only loosely that bell-shaped curve. If we increase that n to 10, we see it start to really become more pronounced. So here we go. See, you can start to see it emerge. And as we get closer to that n equals 50, you can see that it tightens up between, so here it was kind of spread out between 1 and 6. Here it was kind of between 2.5 and 4.5. And here you see it really tightens up between 3 and 4, and it really get that sharp peak, that low up to a high maximum and down the other side. Okay. Let's look at another one. So this is actually a uniform distribution. So in this case, you can see that the values for our n equals 1 are spread out pretty evenly from 1 to 6. As we increase that n to 10, you can see that that shape starts to kind of form, although it's still spread pretty wide across the values here. And then as we get to n equals 50, you can see that bell-shaped curve form once again. And so again, as your n gets larger, your shape is going to approach that standard, or that normal distribution, closer and closer. And then here's what it would look like for a U-shaped distribution. So in this case, it started high and came down the other side. Now, as you increase to 10, you're going to start to see that normal distribution start to emerge. And again, as we get to n equals 50, you can really see it again. So it doesn't matter what the shape of the individual data is, like this n equals 1. It could be normal in the sense that it goes low, it comes down to a high, goes up to a high and then comes back down the other side. Uniform, meaning that it's uniform. And then U-shaped being the opposite of a bell-shaped curve. It doesn't matter. Either way, when you get to this n equals 50, your sample mean shape approaches that normal distribution, that bell-shaped curve. Okay, so an important point, as the sample size increases, the sampling distribution of the sample means approaches that normal distribution. That's the takeaway here. So let's look at an example of how this might come up in a problem. So this problem is about elevators. So suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. Assuming a worst case scenario in which the passengers are all male, meaning that they're probably heavier, what is the chances of the elevator being overloaded? And we're told to assume that male weights follow a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. So there's two parts to this question. First, we're going to find the probability that one randomly selected male has a weight greater than 156.25 pounds. Okay. And then in the second part, we're going to find the probability that a sample of 16 males have a mean weight greater than 156.25 pounds. And if you were to add up that weight, if you had 16 males that all exceeded that weight, they would actually exceed the maximum capacity of the elevator, and that's how it relates back to the problem. Okay, so let's jump into part A. So for part A, we're going to find the probability again that one randomly selected male has a weight greater than 156.25 pounds. So the nice thing for this part of the problem is we're actually using the same methods that we saw in section 6.3. Here we have a we have a normal distribution, but we don't have a standard normal distribution. And so we're going to use our z-score conversion formula, just like we did in section 6.3, to convert that to a z, or to find a z that then we can use in consulting our z-score table to find that percentage, that probability that one randomly selected male has a weight greater than 156.25 pounds. So we're going to plug in the information. For this one male, we're told that their X, so what we're comparing it to, the benchmark, is 156.25 minus our mean. And if we go back here, we'll see that our mean was given to us as 182.9, divided by our standard deviation that was also given to us, right here in the problem, 40.8 pounds. So when we do that, we calculate our z to be negative 0.65. And when we look up that negative 0.65 on the table, and then we do our calculation subtracting that answer from 1, we find that this area to the right, which is the probability of having a weight greater than 156.25, is 0.7422. Okay, so now that we've seen what it is for one man, so roughly a 74% likelihood that one randomly selected male is going to have a weight greater than 156.25 pounds, we want to know what the probability is that a sample of 16 males will have a mean weight that is greater than 156.25 pounds. So just to point this out, in A, we're looking at one man and whether their weight is greater or less than 156.25 pounds. In part B, we have 16 males, and we want to know if their mean weight, so their average weight, is greater than 156.25 pounds. So since the distribution of male weights is assumed to be normal, the sample mean will also be normal. So that means we can assume that our mean and our sample mean here is the same thing. So that 182.9 that was given to us in the problem, this mean, we know we can use here. Okay, now for our standard deviation, we're going to have to do our little calculation, and that was the formula that was given to us earlier in this section, which is going to be our standard deviation of our X. So we're solving here for the standard deviation of our of the mean. So here our standard deviation for X was given to us in the problem as 40.8, and we're told in this part that our sample is going to be 16, so that's our N. So we're going to divide by the square root of 16. And when we do that, we get 10.2 now for our standard deviation. So now we're not at, like we were here, we don't have 40.8 as our standard deviation. We have adjusted that standard deviation based on 16 males to be 10.2. So when we recalculate our z, our new z is negative 2.61. And when we look that up on the z-score table, you can see it here. It's kind of hard to see. But this is actually what we're solving for here. So when we look this up on the table, we see that there is a 0.9955 probability that the sample mean of 16 males will have a mean weight greater than 156.25 pounds or greater. And we found that doing the same exact thing that we did in section 6.3. So while there is roughly a 74% chance, or a 0.7432, that any given male will weigh more than 156.25 pounds, there is a 99.55% probability or chance that the sample of 16 males will have a mean weight greater than 156.25 pounds. So what that tells us in conclusion is if the elevator is filled to capacity, which we assume is 16 men, there's a very, very good chance that the safe weight capacity of 2,500 pounds will be exceeded, which would not be a good thing. Okay, and this last little section here is how you would do a correction for a finite population. This deals with when you're sampling without replacement. Don't worry too much about this, but anyway, this is how you would do that if you saw this come up, but don't spend a lot of time on this correction for a finite population because we won't see this very often. Okay, that ends section 6.5 on the central limit theorem. Up next, chapter 7.